Hello 108 students, Mr. McCue here. We're back at section 10.2 and we're going to keep working our way through here and work on page 4 of our class notes. Okay, got a couple more problems to give a crack at here where you're solving for x is up in the exponent. Example 5c. Going to go ahead and tackle what are we going to do if your parentheses has got a fraction in it as the base. So we've got 2/3 raised to the x equals 9/4. Okay, now you know your goal is to achieve the same base, and we're working with fractions. I look here on the left hand side and I see there's nothing you can do with 2/3. There's you can't take the square roots of it, so I'm going to focus over here to 9/4, and I'm going to realize I could take the square root on both sides of these, numerator denominator, and write 3/2 and raise it to the second, because 3 squared is 9, 2 squared is 4. Okay, now I'm like, well, I have 2/3 and 3/2 and they are reciprocals of each other, and what I'm going to remember now is I'm going to do a flashback over to section 5.1 power rules. We kind of talked about it back there. We didn't make a big deal about it, but we're used to seeing it that if you have a fraction raised to a negative exponent, you're used to working in this direction when you see it. You can write the reciprocal of the fraction. Instead of a over b, you write b over a, so write the reciprocal and change the sign of the exponent from negative to positive. Now what we're going to do here is go from a positive exponent, which we really don't usually care about, but if we go in this direction, we can now take the fraction 3/2, write it as the reciprocal 2/3, and change it from a positive 2 to a negative 2, and that should be a negative 2 there. I just noticed that, so fix it on your class notes there. Okay. Okay, fix that on my notes. Okay, so now we go back here, we swap the reciprocal, take the fraction, write the reciprocal, and change the sign of the exponent from positive to negative. Now we do have the same base, 2/3 and 2/3. That allows us to ignore the base, drop down the exponents, and voila, x equals -2, and you're done. Okay, so we could look at 5b here real fast. This one's kind of interesting. It says 6 raised to the x equals 1/216. You can't do anything over here with 6. You can't take square roots or squares or anything, so I'm going to try to look at 1/216 and realize 6 cubed is 216, so I'm going to write it as 1/6 to the -3. And again, I'm going to turn around and realize that we don't usually say when the exponent is a positive we really want a negative, but I'm going to go in reverse order of taking the base from the denominator up to the numerator and change the sign of the exponent from a positive to a negative. And you can kind of see this work over here. Well, the steps being described. Okay, so we're not used to doing that, but you can. It's just kind of going. Remember, equal signs means you could go both left to right or right to left. Now we finally have the bases the same with 6's. Drop the exponents down, and again, voila, x equals -3, and you're done. Not a whole lot to do there. Once you realize you could take a positive exponent and take it to the other half. Okay, that takes us down to objective 4 here. We're going to wrap up this section. And objective 4 is going to be a few application problems working with growth and decay of exponential functions. If you look at example 6, if you check it in your book, you'll see a bar graph, and we're going to talk about CO2 emissions. On the graph, you'll see time is in x going this way. On the y is CO2, carbon dioxide emissions. Starting off on year 0 was way back 1750. they go, part A asks, what are you going to do in the year 1900? What was the CO2 emissions level? Now you could turn around and look at that graph in your book and see there's a blue graph running kind of like this. I'm just sketching this in. You go up to 1900, hit the blue, and come across, and you're going to see it looks like it's around 300 just by eyeballing it. Now the exponential function is given to us as f of x equals 266 times the quantity 1.001 raised to the x. The key thing to doing these problems is you don't put the year numbers in there. You put how many years are you from 1750, and that's year 0. That's the big thing. You want to leave. This is year 0, year 1900. Subtract 1750 from 1900, and you get 150. It's been 150 years since they start taking data. That's what your x value is going to be. And I've kind of shown the work over here. This is the value you want to use for x. Do not put the years in, count how many years since, and then all you're going to do is get your calculator and take 1.001, raise it to the 150. You're going to look in your calculator, you're going to look for a button that might say x raised to the y. Each calculator is a little different, but play with that until you make sure you get it right, and then you're simply going to plug and chug on your calculator, multiply it out, and you'll see that the answer turns out to be precisely 309 parts per million. Please take a look at that graph and see how much carbon dioxide is happening. Kind of find that turning point and ask yourself, what happened to our society around that turning point? And 1900 was interesting as to see that was kind of the beginning of the turning point, because we had the Industrial Revolution happening. So we started building factories, we started producing cars, combustion engine happened, and so we have been putting many tons of carbon dioxide into the atmosphere. Now here in the year 2012, we've been seriously considering or worrying about global warming. So I just encourage you to get used to looking at graphs. They're very powerful. If you can learn to read graphs and see what the numbers are telling you, you can see trends that are happening. Okay, so with that said, is enough of that. Let's go look at example B. What was the 1950? What was the carbon dioxide? Same idea, same type of problem. You go 1950 minus the 1750 was 200 years since the beginning. That's going to be your x. So you substitute that up into the exponent, same type of problem, and you could see that it's rising. So from 1900 to 1950 in a short 50-year span, the parts per billion went from 309 to 325. Okay, example 7 is going to talk about atmospheric pressure. Working here on example 7, you look at the graph, you're going to see it's a decay exponential problem. Again, they are going to give you the function here, f of x, remember that's y equals 1038 times 1.000134 raised to the negative x. You got to watch that. They're going to say at ground level x equals 0, what would the atmospheric pressure be? So you're going to take 1038 times 1.000134 raised to the negative 0. Anything raised to the 0 equals 1, and so therefore you've got 1 times 1038, and there's your answer. Careful on part B, they say what's the pressure at 5,000 meters? You're going to put a negative in there. Now some calculators can handle that. Remember, you're raising it to a negative. That would be the same as writing 1038. Just gonna see if I can squeeze this in here. Divided by 1.000134 raised to the positive 5,000. So you can either do as a fraction, because remember negative exponents mean you're doing division, and you'll get your answer of 5,031. Okay, that wraps up page 4 of our section 10.2. We're done with it. When I see you again, we'll be working on section 10.3, and we'll be moving along to chapter 10. Okay, I'll see you in 10.3.